So next coming to the beta distribution of the second kind. One second. So when coming to the beta distribution of the second kind, so we will see the statement first. So what is the statement of the beta kind? Beta distribution of second kind is a continuous random variable. So any random variable that should be continuous. So we are taking a x as a continuous random variable is said to be beta distribution of second kind with parameters a and b if the possible probability density function PDF. This is PDF. So the PDF of any continuous random variables with the parameter a and b follows this distribution probability density function. If it is having the probability density function, then we can say it is following, it is said to be beta distribution of second kind. So what is the PDF? We'll see. So what is a PDF for the second kind of beta distribution is f of x is equals to 1 by beta a comma b into x power a minus 1 by 1 plus x power a plus b. Where what is the condition for this? So the parameters a should be greater than 0 and the b should be greater than 0 and x should also, the random variable also should be equals to or else greater than 0. These are the three conditions we will see here. So if these three conditions satisfies, then we can say the random variable we took is beta distribution of the second kind with this formula. Next, coming to the relationship between the distribution of the second kind and the beta distribution of the first kind. So why we are having the two kinds? So we will see what is the relationship between the two. So when coming to the PDF, we will take the PDF first. So we will take the PDF and in the place of y, so we will substitute 1 by 1 plus x. So means what? So in the place of this, we will substitute y. And what happens if this goes this side and y comes this side? So y is equals to 1 by 1 plus x. This goes this side. Means 1 plus x is equals to 1 and this comes downward 1 by y. So 1 plus x is equals to 1 by 5. So when we do differentiation, d of x, when we normal, d of x. So if we do differentiation, it will be like this. So d of x is equals to 1 by y will be minus 1 by y square into dy. Okay. So next coming to this differentiation, again we were taking x is equals to, so from this only we will taking 1 plus x is equals to 1 by y, x is equals to 1 by y minus 1. So what happens when we take LCM for this? So 1 by 1 minus y by y. So when x is equals to 0, if we are taking x is equals to 0, then what happens? It happens like if x is equals to 0, we'll get y is equals. We are taking where like x is equals to 0 and y is equals to 1. So the limits will take x tends to infinity as well as y tends to 0. So we will take the probability density function first, 1 by beta of a comma b integration of 0 to 1 because we are taking the 0 and 1 as the x and y values. So we'll substitute in the integration part. So all this like x by 1 plus x. So what is the x value we are getting? X value we are getting this. So 1 minus y by y power a minus 1. So then 1 by x value can be this, right? So this also we are writing similar to. So y power, when it comes upward, it will be y power a by b. Again 1 by y square, 1 by y square into minus d by. In the place of dx, one second, let me clear. So in the place of dx, we'll substitute this and in the place of 1 by x, we'll substitute y and in the place of x, we'll substitute this. So this three derivations with it. So we are substituting in the main PDF function. Next, coming to when we substituting, so we will do. So what happens? 1 minus y by y power. So this, if bases are same, we can add it, right? So a plus b into this thing and this thing will add. So it becomes integration of 1 to a 0 y power a plus b minus 2 a plus 1 into y minus 1 minus y into a minus 1 into dy. So again, we'll simplify this. A can be cancelled. Minus 2 minus 1. B minus 1 and 1 minus y into a minus 1. So the integrand is the probability density function of the beta distribution of the first kind parameters A. So if we see, this is the thing we are getting. So this is the relationship actually. The integrated, if we are doing the integration for the second kind, then we can say it is the beta distribution of the first kind. We are getting the integration of the first kind if we are doing the integrate of the probability density of the beta distribution. Next, coming to the moments of the beta distribution of second kind. So how we will find, like in the previous classes also we did a lot of moments generating functions, right? So for this we will take mu r dash equals expectation of x per r. So same function we will write, in the function we'll write, and if you do the like previous one beta first kind and other things like in the previous also we did gamma distribution, anything like normal distribution, rectangular distribution, how we are doing the movements there. So the same process will utilize there. So we will use r is equals to 1, we'll use r is equals to 2, and from that we will find out the variance. So it is very easy if you do the same process here also. So expectation of x, the formula, will substitute the expectation of x formula, and we will take r is equals to 1. Then we'll get this one. If we are taking r is equals to 1, then we are having mean value. It means expectation of x is equals to a by b minus 1 for b greater than 1. So the b should be greater than 1, or else it will, if it is less than 1 or equals to 1, then 1 minus 1 or else 0 minus 1, it will be negative value or not calculated value. So it should be greater than 1. So if you are taking r is equals to 2, in the place of r, we'll substitute 2. So in this power, we'll substitute 2, then we'll have the value. This is the value we are having for the mu2 dash. So from this, we will calculate the variance. Variance is equals to what? Variance is equals to mu2 equals to mu2 dash minus mu1 dash whole square. So with the mu1 dash and mu2 dash, we'll calculate this mu2. So this is the thing. So when we are having r is equals to 3, if we are having r is equals to 3, we are substituting the r is equals to 3, then we'll have this value. So from this, we can calculate the mu3 dash and mu4 dash, which are used for the skewness and kurtosis. Actually, you can find out the other things also. Using these formulas, you can calculate the kurtosis or else skewness or else other central fourth and third central movements also you can calculate with this formulas. So you need to remember the formulas. So coming to the Harmonic mean of the beta distribution of the second kind. If x has beta distribution of the second kind, what is the formula? 1 by h, right? 1 by h. It is denoted as 1 by h. So integration of 0 to infinity 1 by x f of x into dx. So in this f of x place, so we'll substitute our PDF function of the beta distribution. So of a second kind. So we'll substitute it in the place of this, how it is. So beta a comma b, actually it can be represented as beta a comma b, right? So but in the place of a, it is a minus 1. So we will substitute that only. In the place of a minus 1, a, we will substitute a minus 1. Beta of a minus 1. In the place of b, we are having b plus 1. So we will substitute like this only. So, and by beta, a comma b. So for this, we are doing the beta function, gamma function we are doing. Gamma function, we are applying gamma function of a comma a minus 1 to b plus 1 by a, b. equals to, we can say B by A minus 1. B by A minus 1. So this is the harmonic mean of the beta distribution of second kind. So what is the harmonic mean of the beta distribution of second kind means H is equals to A minus 1 by B. So where the A and B values, A should be greater than 1 and B should be greater than 0. Okay. Yeah. So coming to the mode, when coming to the mode of the beta distribution of the second kind, we can see if the X is following the beta distribution of the second kind with the parameters A and B, its probability function is no. So this is a probability density function. You need to must remember these formulas actually. So from this only we will calculate the harmonic mean or the mode or the central movements or anything. So PDF probability density function for any distribution is very important to remember. So coming to the mode of the distributions, so we have two conditions for the mode. So in the previous classes also we did same process. So what are the two conditions? It should, if these two conditions are satisfied, then we can say the mode. F of f dash of x is equals to 0, and if we do again differentiation for the f dash of x, then it x double dash of x should be less than 0. These are the two conditions it should satisfy to have a mode. So first we will do, for this we'll do differentiation. So this is formula, UV formula. So we will substitute UV formula here. So U into V minus V into U by V square. So what is U by V? First U into V differentiation minus V into U differentiation by V square. This thing we will do. So like this, we are substituting the values like in the place of x, we are doing the U by V differentiation. So 1 by x whole power A plus B and A minus 1 x power A minus B. Again for this A minus 1 we are doing actually differentiations. Again this will x power A minus 1 becomes x into A minus 2. So same for the similar thing, we will do the same. If we do, this is the formula we'll get if further simplifications. So x is equals to a minus 1 by b plus 1. So where a is greater than 1. So it can be verified that. So after doing this double verification for that, we'll get a minus 1 by, like it should be less than 0, where x should be, the x value should be a minus 1 by b plus 1. This should be like this. So the what is a mode? Then it is satisfying the two conditions. Then the mode occurs at x value what? So a minus 1 by b plus 1, where a is greater than 1. So this is the thing. So we cover this also. So these are all the formulas. It is very easy for you to remember. Next, coming to the Scotchy distribution. So in the Scotchy distribution, if you are starting, so what are the objectives we'll see first. So after studying this unit, you should able to, what we are able to do, we are able to define what is differentiation. Then the important properties of the Scotchy distribution. So what are the important properties we can see with the Scotchy distribution, and consider some important applications where we are using the Scotchy distribution, like we are using some other distributions in the business or else investments. So like this, so in which important applications are there of the Scotchy distribution, we'll see. So coming to the introduction part, the Scotchy distribution belongs to a simple class of the continuous distribution for which the expected value does not exist. So what they are saying is the expected value, what is there, it does not exist. Exists means it does not there. So it was named after the Augustin Scotchy. This distribution has many applications in the risk and finances analysis, physical anthropology, measurement problems. So where we can use the Scotchy distribution? So we can use the Scotchy distribution in the risk and financial analysis, physical anthropology, measurement problems, anything. In these applications, we'll use the Scotchy distribution. So coming to, it is known as Lorentzian distribution in physics. So in the physics, we can say it is known as the Lorentzian distribution, where it is a distribution of the energy and unstable state in the quantum mechanism. So why they call the in physics this distribution means the distribution what we are using the Schottky distribution of the energy is unstable in the quantum mechanics. So there will be some different in the quantum what we can say atom, atomic particles like this. So unstable state is there. So that's why we can say Schottky in this name. So coming to the distribution of this, distribution definition is the continuous random variable x is said to be Cauchy distribution with scale parameter lambda and local parameter theta if the probability density function is given as like this. So what they are saying, we are taking the continuous random variable x and we are saying that it has a two parameters. One is the scale parameter, one is the like location parameter theta. So and the probability density function is what? So 1 by lambda pi into lambda by lambda square plus theta minus x whole square. Theta minus x whole square. So this is the probability density function of the Cauchy distribution. So what happens? The theta value what we are taking should be the integral part of the theta is minus infinity to infinity. So and x is also with infinite minus infinity to infinity. So if these two conditions not work out, like x is not having the intervals of the minus infinity to infinity or between anything, it not satisfying, then we can say zero. F of x, the probability density function of the Cauchy distribution is zero otherwise. So we denote this as x belongs to E of theta, comma, lambda. We can say like this. So denote like this. So this distribution is symmetric about x is equals to theta. So we can say any value x is equals to theta, the same value will come. Since moments of this distribution does not act, in the previous one we did the moments generating central moments, everything, right? In this, the moments of distribution does not exist actually. So where Cauchy distribution with the theta is equals to 0 and lambda is equals to 1 is considered as a standard Cauchy distribution. Its probability density function is this. So what is the function? If theta is equals to 0, we are taking theta is equals to 0 and lambda is equals to 1. Then, so in the this will be the standard Cauchy distribution actually. F of x is equals to 1 by pi into 1 by 1 plus z square minus infinity to infinity is the like integral part of the z. So and if this does not work minus infinity to infinity, then 0 otherwise. When seeing the cumulative distribution function, the cumulative distribution function f of x can be written like this. Probability of x less than or equals to less x equals to integration minus infinity to infinity 1 by pi into lambda by lambda square plus u minus theta whole square into du. So what we are taking u minus theta by lambda, we are considering it as z. So what happens then if we are doing the differentiation, it will becomes du by dz, lambda is equals to dz. Then what happens again? So 1 by pi, 1 by pi, like this 1 by pi, we are taking it out. 1 by pi, we are taking it out. And integration minus infinity to the, what we are taking? X minus theta by lambda as, by lambda as the upper integral part. And 1 by 1 plus u square. 1 plus 1 by u square. Into du as the inside part. Now, so what happens? So this will, if we substitute this, what happens means this is a function of tan inverse actually. So this is the 1 by 1 plus u square into du is the formula of tan inverse actually. This is the formula of tan inverse. So we will substitute the tan inverse. So 1 by 2, we will take this out 1 by 2. If we are doing the integration, 2u will becomes like this. So after this tan inverse of, in the place of du, what is the du formula? It becomes du as x minus theta by infinity. Why? In the place of 1, we are substituting this 1. So this is the cumulative distribution function of the Cauchy distribution. So area property of the Cauchy distribution, if you are seeing probability of mod x minus theta, which should be less than lambda. So what happens? Probability of minus inside we can take like this. We can say minus lambda is less than x minus theta less than plus lambda, minus lambda to plus lambda. So what happens if I take this and this inside? So it will become theta minus lambda minus x less than lambda plus theta. So for one thing, lambda plus theta is one thing and minus lambda minus theta, theta minus lambda is one thing. So these are the two. The same formula in the place in the like we have the 1 by 2 1 by pi into tan inverse right, that value, so we'll substitute that value here. So 1 minus in the place of that we'll substitute 1 by 2, so we are substituting, then we are getting value as 1 by 2. So if we are taking it is less than minus 2 lambda, in the first one we took less than lambda, right? So in the second one, we'll do less than 2 lambda. Then we'll get the value approximately 0.7048. If we are taking it is less than 3 lambda, then we are getting answer as 0.952. 0.952. Okay. Next, coming to the characteristics functions of the Cauchy distribution. X follows the standard Cauchy distribution. Then, so what is the value? So it is represented as pi of x is equals to expectation e power itx. So we know what is itx. In the place of itx, we will like this only. F of x can be represented as what? Integration part of f of x, right? In the f of x value only, we are writing this 1 by lambda into 1 by x, 1 plus x square. So they did not mention the thing that expectation of x can be written as integral part of the f of x. So we need to write that part. After f of x we do it. So inversion theory. So what is the inversion theory of the characteristics theory? Means this will be inverse. Like this thing will becomes f of x is equals to 1 by 2 pi integration minus infinity to infinity e power minus itx into pi x t into dt. So this is because of the inversion theory. This is because of the inversion theory. So where f of x is the probability density function. So what the f of x is the probability density function we know of the Cauchy distribution. Then this pi x of t. This pi of x of t is what? It is a characteristics function. For the Laplace or double exponential distribution, this becomes what happens for the double exponential distribution 1 by 2 e power minus mod, where the x value can be minus infinity to the infinity, minus infinity to infinity. So this is f of x. Then for the pi f x of x, it will become as 1 by 1 plus t square. 1 by 1 plus t square. For applying, for again, we are applying this. For this, we are using the inversion theory. This becomes, again, inversion means this comes backward, again, back direction. So 1 by 2 pi into integration minus infinity to infinity power minus itx into 1 by 1 plus t square into dt. Again, for this, 1 by 2 can be, this 2 can be cancelled easily. So this becomes expected e power minus small x equals to 1 by pi into minus integration minus infinity to the infinity e power minus itx into 1 by 1 plus t square into d. So what happens when we interchange t and x? Then in the place of x, we'll substitute t. In the place of x, we'll substitute t. And in the place of t, we'll substitute x. So we are interchanging the x and t in the characteristics function. So in the place of if we take minus t in the place of t. So after exchanging t with the x, we'll substitute minus t in the place of t. So what happens in the place of t minus t? We'll substitute this. So from the first in the previous equation as well as this equation, we can conclude that phi of x of t equals to e power minus tx. The same value we'll get actually if we interchange that also. So two parameters if you are taking this theta and lambda of the Cauchy distribution. Not sum of any individual Cauchy variate is also a Cauchy variate. So if you are taking the number of independent Cauchy variates and doing, you will get the Cauchy variate only. Next, coming to the median of the Cauchy distribution. When coming to the median of the Cauchy distribution, so where if M is the mean of the distribution, it means probability of X less than or equals to M. We are taking probability of X less than or equals to M. And probability of equals to probability of X greater than or equals to M. What both probabilities is equals to the 1 by 2. So considering first part, we'll consider what is that first part? X less than or equals to M. So less than or equals to M equals to 1 by 2 we'll consider and we'll see. So these are the four codes. So integration part minus infinity in the lower boundary as well as M in the upper boundary we'll take. So f of x, so in this place, f of x into dx. So we know f of x. So what is f of x? 1 by lambda, 1 by pi into lambda by lambda squared by x minus theta into dx. Integration minus infinity to M. So in this x minus theta by lambda reciprocal 1 by u, this will becomes. So we are taking x minus theta by lambda is equals to u and dx by lambda is equals to du. So what happens? This is reciprocal of this actually, right? So we'll substitute 1 by 1 plus u. Actually, this is u. 1 plus 1 by u and du. So after du, then again this thing becomes what? M becomes m minus theta by pi lambda. So in this, I told 1 by 1 plus mu square is the formula of the tan inverse, right? We'll substitute the tan inverse here. So 1 by 2 is equals to 1 by 2 plus tan inverse m minus theta by lambda. So this becomes same. Tan inverse goes tan. So the median of the distribution is what? M. The theta is equals to M. So the median of the distribution is M. Then coming to the mode of the distribution, mode of the Cauchy distribution. If mode of the distribution exists, then it will be the point where, and the previous also we did the same process for the every question you need to do. So two conditions you need to check. F dash of x is equals to 0 and f double dash of x should be less than 0. These are the two conditions you need to verify. So for the Cauchy distribution, f of x, we'll take PDF first, PDF function. I'm sorry. So f dash of x is equals to 0. We will equate this with the 0. We'll equate this function with a 0. Then lambda is equals to theta. X is equals to theta we'll get. So after equating this. So again, if we do double differentiation, we'll get the value as less than 0. So it means two conditions. So where we are taking the mode of the where it occurs like two conditions are satisfied, we will take that as a mode. So the mode is equals to x is equals to theta. So x is equals to theta. Okay. Next, comes to the quartile deviations. The first and third quartiles of the distribution satisfies. So we are taking the first and the third quartiles distributions. Two things we are taking. So this is the new topic, right? From the previous distribution. Yeah. So what happens? Quartile means first and third means 1 by 4 and 3 by 4. Means first quartile means first one, Q1, and third quartile means Q3. So P of probability of X less than or equals to quartile 1 equals to what? 1 by 4. And the probability of X less than or equals to quartile 3 is equals to 3 by 4. So third quartile it is 3 by 4 and first quartile it is 1 by 4. Next, consider the first thing. We'll consider this first thing and we'll do. What is the thing we'll get from the first quartile? We'll see. So for the first quartile, for infinity to infinity actually, but infinity to the quartile 1 will take, and f of x into dx equals to 1 by 4. So same, in the place of x minus theta by lambda is equals to mu, though this can be inverse, like we will get 1 by 1 plus u square, 1 by 1 plus u square into du. So equals to 1 by 4. So we will change quartile 1, q1 integration upper boundary as q1 minus theta by lambda. So in the place of this, so it looks like what? Tan inverse formula. So tan inverse formula we'll say. So this becomes 1 by 2 plus 1 by lambda into tan inverse of this q upper boundary q1 minus theta by lambda. So this is equals to what? This is equals to 1 by 4. This is equals to 1 by 4. So this is equals to 1 by 4. So 1 by, so again, from this simplification, what happens if this goes this side? So 1 by 4 minus 1 by 2, it becomes minus 1 by 4. This thing will be same. So tan inverse, right? If this goes this side, uh, tan of minus 1 by 4 into this 1 by lambda into lambda, then it becomes minus 1. So minus 1 actually. So minus 1, what happens? So if this goes this side, means q1 quartile 1 minus theta by lambda equals to 1 minus 1, right? So I'm sending this. So quartile 1 is equals to 1 minus lambda. Then I'm sending this also. So quartile 1 is equals to theta minus lambda. Theta minus lambda. So this is a quartile 1. The same similar manner we'll do for the quartile 3 also. I'll show you that. So if we do the same manner, if we do the same manner for the quartile 3 also, what we'll get? We'll get the values theta plus lambda. In the quartile 1, what we got? Quartile 1 is equals to theta minus lambda we got. In the quartile 3, we'll get theta plus lambda. If we do theta quartile 5, then again maybe it comes as theta minus 5, theta minus lambda. So quartile deviation half 1 by 2 into Q3 minus Q2 equals to lambda. So this is a quartile deviation. So quartile deviation is that. So a two-parameter Cauchy distribution, median is used to estimate the location parameter. So, we know location parameter is theta, and quartile deviation of the semi-interquartile range is used to estimate the scale parameter. So this quartile deviation is used for the scale parameter, as well as Cauchy distribution median is used for the location parameter to find out the location parameter. Next, coming to the moments of the Cauchy distribution does not exist actually. So we have a standard Cauchy distribution, right? So we'll do. So first one we'll do expectation of x. So it can be written as integration of minus infinity to infinity x of x into f of x into dx. So in the place of f of x, we are substituting the f of x value. So after f of x, we will take this outside. So it becomes lambda by uh, pi integration minus infinity to infinity. So this can be written as, how it can be written as means x minus theta plus theta. Means this theta, if theta can be cancelled, minus theta plus theta, right? If we are cancelling minus theta and plus theta, again we are getting the x only. So for the simplification derivation, we will use plus theta and minus theta. We are adding plus theta minus theta. So after that, lambda square plus x minus theta square will be similar. So after that, again this theta can become outside. So what happens? Theta into x by lambda equals integration minus infinity to infinity dx into, one thing we'll do, dx into lambda square plus theta minus theta, x minus theta whole square. This again we'll do it as a separate one. So for both things we are doing, for this thing one and this thing one. So actually what happens for this? Lambda by x, lambda by pi minus infinity to infinity theta by x square plus x minus theta whole square as 1. And again plus lambda by pi integration minus infinity to infinity x minus theta by x minus theta whole square. Again, we know from this we can cancel one x6, right? Like this we are doing. So this pi can be comes outside. That's why first one we will having this. So this is from the previous one. Next. So what happens? Theta into lambda by pi integration dx by x square plus theta minus x minus theta whole square and this. So in this place of this, we are substituting z. So what happens? X minus z theta is equals to z, right? In the previous one we do. So we'll substitute z. So z by lambda square plus z square 1 by pi plus this becomes theta into 1. This becomes theta into 1. So, but z by lambda square plus z square integration minus infinity to infinity does not coverage completely. Like it does not converge, right? So it does not converge. So that's why we are seeing this distribution is does not having the distribution movements actually. In the general sense, the mean of the Scotchy distribution is does not exist. What they are saying, it does not exist. Next, coming to the relationship, coming to the relationship. So relationship with the other distributions. So what is the relationship with the other distributions? We'll see now. So if x is a standard Cauchy variate, then if y is equals to x square has a beta distribution second type with parameter a is equals to 1 by 2, b is equals to 1 by 2. So a is equals to 1 by 2 and b is equals to 1 by 2. So if x is a Cauchy variate, then y is equals to by x square has a beta distribution on matter. So the parameters, what it becomes? The parameters becomes a is equals to 1 by 2 and b is equals to 1 by 2. So if x and y are two independent standard normal variates, u is equals to x by u. This also follows the Scotchy distribution only. This also follows the Scotchy distribution. And x has the uniform distribution or rectangular distribution on it having the parameter of lambda minus pi by 2 and pi by 2, then the y value becomes tan x and it follows this value. Y is equals to tan x follows the tan x Cauchy distribution. This is the relationship. So these are the relationships. So this is very a small distribution actually. So now it is very important the application part. So we completed all the things like rectangular normal distribution one, normal distribution two. So in this from now we'll see how to implement that part in our real-time examples. Like not real-time examples. If you are having any example, any question, so how to solve it. So we will do now. So this is the application, totally applications part now from now. So applications of the first one, we are doing applications of the rectangular distribution. Uh, so coming to the applications, what are the objectives means after doing this chapter, identify what is the rectangular distribution, then apply the rectangular distribution property to solve the given problem. For the given problems, we'll use the rectangular distribution and will properties and will solve the problem, and we'll find the probabilities of the given intervals also. Probabilities of the given interval also we'll find out. Okay, coming to the first example, we'll see how we are doing. Coming to the application problems. So what is the question here? So if f of x is equals to 1 by theta, if f of x is equals to 1 by theta, and what is the x value here? 0 is less than or equals to x, and x is less than or equals to theta. And show f of x is a probability density function. This f of x is a probability density function, and also find the moment generating functions and moments. So these are the things we need to find out. Show that we need to first show that f of x is a probability density function. Again, that we need to find the moment generating functions and moments. So first, what we have taken from the example that given f of x is equals to 1 by theta, where theta 0 is less than or equals to x, x is less than or equals to theta. So clearly we can say f of x is greater than or equals to 0. If you are taking f of x greater than or equals to 0, what happens? So from the 0 to infinity, right, we have the integral part. So we'll use that only. Integral f of x is equals to, in the place of this, integration of 0 to theta. Just simply for easy to only, what we are doing means f of x, we are using the integral part. Integral part. What is the integral part? Theta to the 0 to the theta. So integration 0 to theta, 1 by theta into dx. So what happens for this? So the 1 by theta comes outside, integration of 0 to theta into 1 into dx. So 1 becomes as x. So 1 by theta into x into theta 0. Differentiation will do. So one time we'll substitute 0. 1 by theta into 0 minus theta minus 0. Theta minus 0. So theta minus 0, what happens? 1 by theta into theta. Theta theta cancels 1. F of x into dx is equals to 1 unity. So we can say easily f of x is a probability density function. Since x follows the normal distribution, means a continuous random variable is following the normal like uniform distribution or else rectangular distribution with the parameters what? Theta and 0. 0 and theta. 0 comma theta. So then it's moment generating function. Now first thing we said f of x is a probability density function. Now we are finding the moments generating functions. So what is the formula for the moment generating functions? How it is denoted? So it is denoted as mx of t. Mx of t. Mx of t. So mx of t. So mx of t. So mx of t can be written as how? Expectation of etx. Expectation of etx. So expectation of x can be written as what? X into f of x integration, right? So we are writing expectation of x as integration 0 to theta e power tx into f of x into dx. So what is f of x? We are having 1 by theta f of x we are having. So in the f of x, we will substitute 1 by theta. So for this, we are doing the integration part. So the 1 by theta again comes inside. So e power tx integration 1 by theta integration 0 to theta into dx. So for this, what happens if we are doing the integration part? E tx by t. It becomes etx by t. Etx by d if you do it differentiation. So etx by t. In the place of t, we'll substitute in the place of x will substitute 0 one time and t one time. So what happens if you are substituting the x is equals to 0? It becomes e power t x theta minus x. So what happens for the x e power t e power t theta can be written as how? It can be written as 1 plus t theta. Then again t theta by 2 factorial whole square plus t theta whole cube by 3 factorial. Like this, so on can be represented. So t power tx can be written as like this minus 1. So 1 by theta t into again this 1 and plus 1 can be cancelled, right? So this is the 1. So mx of t is equals to what? Moment generating formula 1 plus theta t t theta by 2 factorial plus t theta whole square by 2 factorial plus theta t whole cube by 3 factorial and so on. So which is moment generating function of the given functions. So in the third one, what they asked to find out the moments also. So we'll find out the moments now. So what is the formula for the moments? Expectation of x. For this, with respect to t, we'll do the differentiation and we'll keep t is equals to 0. So if we keeping t is equals to 0, what happens? 0 differentiation of 0, 1 can become 0. So in the place of t, we are keeping 0. Again this t square 2t becomes t can becomes 1 and clearly 1 becomes 0 and t becomes 1 if you are doing the differentiation. T square means 2t, it will become t cube. T3 square becomes. So this is the, if we are doing the differentiation part. So after that, what we can conclude, this is a 2 factorial, like, so theta by 2 factorial, theta by 2 factorial. So what is the function? Moment mu 1 dash is equals to theta by 2. Mu 1 dash is equals to theta by 2. So if you are doing the expectation of x square, same will do double differentiation actually. Double differentiation for this. So this is the thing, right? For this, we'll do the double differentiation. So this 0 becomes 1, 1, and this 1, it becomes 2t into theta square. This t becomes 1. This becomes 0 0, it's gone. So 0, so t becomes 1. Okay, 3t square means 3 t square becomes what? 6t, 60, 60. And again so on, if we take 12t, 4t cube, right? 12 t square, it becomes 12t square. So from this, what we can conclude, it is 2 theta square by 2 theta square by 3 factorial. It continues. So that's why factorial. I think you understood. So what is the value we got? So we got for second one. So mu 2 dash is equals to theta by theta square by 3. So what happens when we take the mu 3 dash? Same double differentiation will do. Then it becomes this thing. And again for this becomes 0. And I'm sorry, first thing becomes 0 and second one becomes 6 theta cube t. T becomes 1. And for this, it becomes 24, means t square, right? 24 theta power 4 t by 5 factorial. From this, what concludes we can do? So 6 theta cube by 4 factorial. Theta cube by 4 factorial. And this becomes 0 and this also becomes 0. So what we are getting? Mu 3 dash is equals to theta cube by 4. Theta cube by. So again, I think you can do the fourth one. So fourth one will get theta power 4 by 5. So anything common we are seeing. So mu 2 dash is equals to, we got theta square by 3, I think. Yeah. So mu3 dash is equals to theta cube by 4 we got. Okay. So mu4 dash is equals to what we got? Theta power 4 by 4. Any similarity we can see, so we can see. So if you are assuming these are the theta power r, so theta power r, so in the down, what had happened? Theta per r means r plus 1. So theta per r by r plus 1. So we can think 1, 2, 3, so on. So this also can be written as mu r dash. So all odd order and the even order movements generates. So this is the problem solving. So we have a lot of examples also. Second example will complete. So if x is a random variable with a continuous distribution x, then f of x is a uniform distribution of 0, comma 1, we need to prove it. So how we need to prove it? So f is a distribution function and non-decreasing we are assuming, and y is equals to f of x. Then what happens? G comma of y is equals to what? Probability y less than or equals to y. So y can be written as how? F of x. So again, for gamma g of gamma of y is equals to p of x, and in if this goes this side, f goes this side, so f becomes f dash, f power minus 1 into y. This is the inverse. If you are taking the inverse, this is the inverse. So f is a non-decreasing and given to the continuous. So this is the g of y equals to f into f power minus 1, means we can say f inverse into y. So f is the distribution function of y. What happens? This f and f inverse can be cancelled. F inverse means what? F by f. F inverse means 1 by f, right? So f and f inverse can be cancelled. So what it becomes? It is equals to y. So the probability density function of y, f of x, is given as how? So g of gamma of y is equals to y of, sorry, g of y is equals to d by dx of g of y of y equals to what? We are getting it as 1. The value is equals to 1. So if since f is a distribution function, y takes the values in the range 0 and 1. So what the values it is taking? It is taking the values of 0, comma 1. 0, comma 1. Since g of y is equals to 1, and g of y is equals to what? G of y is equals to 1. And the values of y is 0, less than or equals to y, means x is greater than or equals to 0, and it should be less than or equals to 1. So these are the conditions. So y is a uniform variate on 0, comma 1. So these are the things we covered today. So what are the things we covered? We'll have a glance. So we covered the beta distribution second kind. We completed. Beta distribution second kind we completed. Cauchy distribution we completed. So after Cauchy distribution, what one we completed? Cauchy distribution is completed. Again, we started the applications of rectangular or uniform, rectangular and uniform uniform distribution. These are the things we covered actually. I hope you understood. So in the next sessions, we'll complete the remaining examples also. What are the remaining examples? We have 3, 4, 5, uh, 5 are there. Like remaining 3 are there. So we'll complete the remaining 3 and we'll go for next thing. So applications of the normal distribution will go. So we have more 3 to cover in the uniform distribution. So in the next session, we'll complete the 3 and we'll go for the examples, applications of the normal distribution. Thank you.